In this tutorial, we are going to use the PBMSECT entry to define a arbitrary beam cross-section composed of a composite laminate. My name is Christian Aparicio, and I'll be going through this tutorial with you today. Now, this is what we have. We want to take this existing beam element that is composed of the traditional isotropic material. If you look at the cross-section, this is a regular box cross-section, if you will. We want to create a new arbitrary beam cross-section, but we want to use some existing PComp entries to define the walls of this cross-section. So here, by the end of this tutorial, this is pretty much what we're going to build. Again, we are going to use MSC Nastran's PBMSECT entry to define this composite beam cross-section, if you will. Now, let's see. One thing before I start, just in case you have any questions, comments, feedback, if you have questions regarding Nastran SOL 200 training questions, optimization questions, whether or not you're using a SOL 200 or you're using machine learning, if you want access to the SOL 200 web app, these are all things you can come to me and ask about. So here on the screen is my email. Let me go ahead and exit here and jump to the SOL 200 web app. So to start off with, let's go ahead and open up the user's guide and download our starting bulk data file. So if we go to the SOL 200 web app, if we open the beams viewer, we can import this bulk data file. The latest version of the SOL 200 web app has a lightweight beams viewer that will help you look at what the cross sections of your beam elements look like. So here, this is pretty much showing you what these bulk data entries have. So we're using a MAT1 entry for an isotropic material, and we are actually showing you a PBM3 cross section here in this view. We're actually showing you CBEAM elements. If I turn on the labels for the elements, and if I zoom in very closely, this is, let me turn off the beam shape. This element is beam 4, which corresponds to CBEAM 4. So the beams viewer can support and display CBEAM 3 elements. Let me go back now to the size web app and open the PBMSECT web app. We're going to upload this bulk data file to the PBMSECT web app. So let's go ahead and do that right now. And click upload. If you notice here, this bulk data file has existing PComp entries. We are going to use these PComp entries in a moment. Let me click create new entry. Now, whenever you're dealing with a composite arbitrary beam cross-section, keep the following in mind. Number one, you should only be using CBEAM 3 elements. That's number one. Number two, only the PBMSECT entry is supported for the composite arbitrary beam cross-section. Here, when you specify the core field, click yes. This is going to trigger the core keyword in the PBMSECT entry. So first, let's go ahead and define the points of the cross-section. Let me look at the tutorial. Now, I should mention the tutorial is available in the user's guide here in the column PDF. If you click link, this opens up that PDF. If we go through some of these slides, and here, let me look through my notes. What I want to look at is approximately how big is the cross-section we want to define. Okay. Let me jump back to the PBMSECT web app. The cross-section is about 20 units of length for the width and height. These units of length will be the same units of length that you use for your bulk data file. So here we're using units of millimeters. I suspect this might be a little bit different though. Actually, this might be a mistake in this example, so ignore this. I forgot, let me see, MAT8. I actually did not include what the units are, so I'll have to get back to you on what the units are for the length at least. But know that here for the width and height, these units of length will be the same as the units of length in the bulk data file. Let me go ahead and now take some time to create the points for the cross section. And now let me go ahead and connect the dots here. So let's go ahead and click these points. And then to finish off this cross section, I'll click these points. And let me go ahead and click select lines of outer perimeter. Remember, I always want to take, in most cases, I want to select the outer lines as the outer perimeter. Now, one comment, whenever you're building your cross section and you're going to build a wall from outer perimeter to outer perimeter, I always recommend, building at least 2 lines when you're going from outer perimeter to outer perimeter. If you use 1 line, this sometimes creates issues. Here, let me make sure things look okay. And let me look at my PBMSECT entry. Okay, things look okay so far. Now, here in the line section of this tool, this is where I could get to now use those pcomp entries that were in the original bulk data file. The default pcomp entry for all the lines will be set as pcomp501. If we turn on the preview, this is what our cross section looks like so far. Now, here, let me turn on the isometric view. Each line is going to be given a ply coordinate system. This ply coordinate system determines the direction that the plies are going to be stacked. Now here, for this line, the up direction is actually pointing downward, but I want the up direction to point upward. So here what I can do, and this will only work if you set the section as a closed profile section. So let me go ahead and do that. So here, after I made the modification, you'll notice that the ply coordinate system has switched. So now the blue ply coordinate system line is pointing upward. If I ever want to adjust this, I can go to the custom ID section. I can click renumber lines and points. And then let me turn off the preview. And this typically, and I did it now, this will typically switch the numbering of the labels. So here, this is 0.1, 0.6, 0.5, and so on and so on. When I click renumber, the numbering is switched, which causes the ply coordinate system to also switch. So, okay, let me look at my notes and let's continue on. So here, let's turn on the top column. For some of the lines, I want to add an additional set of plies. So here, I want to add pcomp502. So here, for line 1, we've added these additional lines. Let me turn that off again. Let me turn it on again. You see that for all the outer perimeter lines, I'm adding additional plies. So here, and this is what we have. Now, for this middle wall, if you will, I want to modify the default laminate use for that line. So let me go ahead and use pcomp503 for these 2 lines. So now if you notice something here, the ply with 0 angle plies, if you will, is running in the interior of this cross section. So here we have 0 degree plies here, here, here. The next ply, if you will, the orange ply, and these are 1 degree plies. So we have a 1 degree ply running through here. So it's important when you're building your composite section that you have this set of consistency. Generally, anything below the center line has to be moved across to these branch lines, if you will. If you do not follow this rule, and these rules, all of these rules are mentioned in the tutorial file. So if you're ever going through this process where you want to build your own composite arbitrary beam cross section with the PBMSECT entry, I refer you to the appendix of the tutorial, because this has a lot of guidelines to successfully build this. So again, going back here, anytime you're going from the outer perimeter line to a branch line, you want to maintain the same number of plies. So here below this blue center line, there are 4 plies. When I go to this branch line, I also have 1, 2, 3, 4 plies. Also, I haven't confirmed this, but I'm pretty sure this is a requirement. The thickness of the plies should also be identical when you're going from an outer perimeter to a branch. Let's see, what else is there to do? I think things look good. Let's run MSC Nastran and see if we successfully generate the cross-section. So here, you notice a few things. The cross-section looks completely different. Things do not look okay. So this could be due to many reasons. Here, let me go ahead and investigate a little and see if we can identify why this is happening. Okay, so this is point 1, 2, 3, 4, 5, 6. Let's see, I have point 7, lines 8 and 7. Let me eyeball the entry and see if I can determine what's going on exactly. Oh, right. Well, maybe not all right. Sometimes I know that. Let me look at my notes. When you build these composite arbitrary beam cross sections, the process is very delicate. So I think here for one of the points, I forgot to add this small offset. So let's go ahead and look at what that point is. Okay, let me add this. So let me offset this a little. So instead of a value of 0, let me use 0.0001. Let me look here. Okay, let me try running this again and see if we have a success. I suspect that it was not successful, so let's see if we could look at this a little bit more. Now, things look a little better than before. I'm still not satisfied with how things look, and if we look at the preview, we'll notice a few things. Let me look at the actual cross-section. You'll notice that there are these weird angles, and this to me is a very suspicious thing. Let me download these entries for a moment. So we'll go ahead and download this bulk data file. We'll create a test folder, if you will. I'll move this test file here, and I will run MSC Nastran for that test file. Here, let me open Patran. And when you run Nastran, you get this PostScript file. If you have Adobe Acrobat, you can use Adobe Acrobat to create the PDF file. In this PDF file, we get the cross-section displayed. And you'll notice that there are a few issues with this cross-section. There are these kinks, if you will. I'm going to open Patran rather. When you run Nastran, you get this additional file. This file has the mesh for that cross-section. I'm going to use Patran to import that mesh. So this would be model ABCS and beam 9. Let me click apply. And then if we look at the ZY view, this is what we see. The mesh doesn't look very healthy at this point. If I turn on just the free edges, you see that this cross-section, in my opinion, is not suitable. We have to somehow identify what the issue is. So let me go ahead and go back to the PBMSECT web app, and let me see if I can identify what is the issue. So this is 1 through 6. So 1, 2, 3, 4, 5, 6. So that would be this set 1, which corresponds to the outer perimeter. Set 902 and 903. So it would be 3 to 7, and then 7 to 6. Okay, looking good so far. And this set 904, which I believe was the layer, the top layer. Let me click renumber. Okay, so now the plies are going upward. Let me run MSC Nastran again and see if I get something a little better. Okay, looking good so far. I'll explain in a moment what was the issue. But whenever you're dealing with composite arbitrary beam cross sections, I recommend doing this. Always download the test bulk data file. Always manually run this file. Let's go ahead and run MSC Nastran. And always open Patran and make sure that things look okay. It's very easy to create a cross section that has a few issues like this cross section. So I always recommend doing this check. So let me go ahead and show you what the process is like here. Let me go ahead and import this new bulk data file. And let me look at the mesh for a quick moment. Okay, this is a lot better now. Let me turn on the free edges of this model. There we go. This looks way better than it did before. Now what I can do here, let me create some groups from the different properties. If we open up that bulk data file, remember this bulk data file contains the mesh for this cross section. The angles are stored in a sort of awkward way. The angles for the different plies are stored in these P shell entries. So here, ply 1 has 0 degrees, ply 2 is 1 degrees, so on and so on. But some of the plies are using negative angles, and we're using P shell values, the thickness field, to store the angle values. It's a really awkward situation, but hopefully makes a little sense. Here, for example, a negative angle of -5 degrees is being expressed as positive 175 degrees. If I had an angle of -9 degrees, that's being expressed as positive 171 degrees. If I look back here, I've just created a bunch of groups. So let's go ahead and display all these different groups. And let me display the original edges. So let's go ahead and go back here. Now let me turn off some of these groups. And what I want to do now, let me turn on the thickness plot, show thickness, and click apply. So now we're looking at the different angles for these different plies. So plies 1, 2, 3, and 4. Just be careful. If you turn on too many plies, and if I go back here and update it, remember that negative angles are being offset by positive 80 degrees. So what was previously -5 is being expressed as 175. This throws off the thickness plot that you see here. So always be a little careful. Here, let me go ahead and zoom out and let me display these plies. And let me update the thickness plot. So here, so you see that the ply with 0 degrees is continuous in the inside. The ply with 1 degree is also continuous. Now let me turn off some of these. Let me show you the outer plies right now. And I think I've turned too many on. Okay, perfect. So here, remember, these are the plies that we have stacked on top. So if you look at the thickness fringe here, if you will, these are angle values, positive 175 down to positive 172. Right now, what we're looking at are these turquoise, slightly yellow, gray, and pink. These are the plies that we're looking at right now in Patran. So I always recommend downloading that test bulk data file. I recommend running Nastran to generate this equivalent finite element model of the cross section. If you have access to Adobe Acrobat, use the PostScript file to generate the cross-section, and then visually confirm in Patran to make sure that you don't have any odd cross-sections like we had here a moment ago. Now, what was the issue before? Let's look back here and let's renumber the points. So right now it's just 0.23, click renumber. Now my ply coordinate system is pointing a little differently. Remember that this blue ply is corresponding to ply 0 degrees. This turquoise color is corresponding to ply -9 degrees. Remember, when you're going from the outer perimeter to a branch, this interior ply should be continuous with the next ply. But here we go from -9 degrees to +0 degrees. This is the issue that was causing this really odd cross-section to be generated. So here, if I were to run MSC Nastran for this cross-section, you're going to see those kinks that I mentioned a moment ago. So here, these are the kinks that are generated when you have this discrepancy with the cross-section. So here, that's what that looks like. So again, this is because we're going from a -9 degree ply to +0 degree ply. This throws off the algorithm in MSC Nastran. But if I click renumber lines, let me zoom out so you see what that looks like. So 165, click renumber. So now this is 2, 3, 4. And if I run MSC Nastran again, we should have a better looking cross section. And if we look at the plies, for line 2, we have a ply of 0, which goes along with the next ply of 0 degrees. Now, let's see, what else is there to do? Let me look at my notes. I think that's pretty much it for this. Let me go ahead and download the updated bulk data file. So let me extract this. And there's one adjustment we have to make. So the existing CBEAM3 is pointing to a PBMECT with ID 8. So this is going to be an issue for us in a moment. Where is that PBMECT? Okay, here. Maybe we want to renumber it. So PBMECT388. Now, we want this CBEAM3 to use the new PBMSECT entry. So remember, this is looking for an entry with ID 8. If we go back here, we're going to change the ID to 8. So now this CBEAM3 element is using this arbitrary beam cross-section that's using the composite laminates defined through the PComp entries. So let me go ahead and run Nastran to do a final confirmation that this bulk data file is good to go. Let's go ahead and click run. And I expect things to go okay so far. So let me click here and let me search the F06 file for any fatal entries. Okay, things look good so far. After there are no fatal entries, let me make sure that I actually get structural responses. So here I get forces and I get displacements. So this looks okay. This is a good to go bulk data file. If I go back to the beams viewer, let me actually show you what this CBEAM3 looks like with the new arbitrary beam cross section. So let's go ahead and select that updated file. And this is what the beam element looks like now. So remember, this is a CBEAM3. At the beginning, we started with the regular PBEAM3 entry, but now we've used the PBMSECT entry to define a cross-section composed of different composite plies. If we wanted to, let me go ahead and close out everything. You might be wondering, okay, what if I want to maybe close everything, leave for the day, and maybe come back tomorrow to continue my work? How do you update the bulk data file? Go and open the PBMSECT web app. In this folder, remember, this new updated bulk data file contains our arbitrary beam cross section. Let's go ahead and upload this bulk data entry. And we just click upload, and now we can continue our work. Maybe you want to adjust one of the points. Maybe 10 wasn't good. So maybe here I've adjusted it so it's 12, maybe 15. Maybe you want to use 15. You can make your adjustments here. You can go run MSC Nastran. You can make sure that things look okay. And here, this is what my new arbitrary beam cross-section looks like. I can go ahead and download my new set of bulk data files. Since MSC Nastran doesn't like spaces or special characters, I'm going to remove spaces and parentheses. I'll skip running MSC Nastran since I'm confident that file is okay. Now here, I'm going to upload this updated bulk data file. And then in a moment, you should be seeing the updated bulk data entry. So there you have it. That's how you can build a composite arbitrary beam cross-section through the use of the PBMSECT web app. I defined a PBMSECT entry. I defined the core keywords. The core keywords point to the pcomp entries. So here, pcomp 501, that's being referenced by this keyword. Core 7 is using pcomp 503, which is this pcomp entry. So I've gone through the process of how to define, how to confirm your cross-section looks okay. The second thing I did, say you leave work for the day and you come back the next day. If you want to make edits to the arbitrary beam cross-section, what does that process look like? You basically come here again, you upload your bulk data files, and you make your adjustments. And here I went all the way to the point of showing you the new updated cross-section in the beams viewer. The one last thing I want to leave you off with, it's very tricky to define a composite arbitrary beam cross-section, but this tutorial has a lot of information how to properly define your cross-section, and the appendix of this tutorial has various comments on how to understand the ply coordinate system, what to look out for, how to prevent certain issues when defining the cross-section. I spent a few hours with this, so I hope all the information contained in this tutorial will help you have success when defining your composite arbitrary beam cross-sections. Now, the one last thing I want to leave you off with, as always, if you have any comments, questions, you're always welcome to contact me at this email address. Thank you so much.